So if it messes up, it's his fault, okay? Daniel's fault, okay?
Alright, sounds good. Okay, so last time we started talking about the determinant and indeterminate structures. Just for your information, most of the structures out there are indeterminate. There's some determinate structures out there, but most of the structures out there are indeterminate. Like the structure that we are in right now, it's definitely indeterminate because it has lots of columns, and these columns are attached to foundation. Each foundation can be fixed or hinged, so you have a lot of reactions that can take care of this structure. Okay. However, some structures they look. Have you guys seen those structures that are, like some on the internet? If you guys saw them, like one big column is going up there, and the structure is whole. So it's just one column fixed in the ground, has 3 reactions or has 6 reactions because X, Y, Z and moment. So it's like, because it's a space structure, not 2D frame, but it's kind of look like as determinate structure, right? However, most of the applications that are out there, they are indeterminate structure. So I'm gonna refresh your memory, solving some example just to make sure that everything's okay. I'm gonna solve 2 examples very quick. So let's put the first one as a structure like this. All right, and this structure is hinged roller, and I'm asking you to determine the degree of a static indeterminacy. So I'm gonna say IS, and I'm gonna have another structure, and this structure is like this, and the same thing, I'm asking you to determine the degree of static indeterminacy. So let's solve the 2 structures. Just like to make sure that you guys understand the concept of internal and external. So from what we see right now, this is a closed structure, right? So definitely if there's a closed structure, that means that there is internal indeterminacy, because internal indeterminacy is showing because you have closed vents. If you have an open structure, I don't think you would have any internal indeterminacy. And internal indeterminacy, that means that there's members that are excessively in the structure, that the structure doesn't need to be stable. Like if I take this one out, if I take this one out, the structure is gonna be okay. And to solve the structure, I have to cut in these members, all right? Okay, so let me connect these 2 again. And the first thing that we do in these kind of problems, what we do, first we calculate the M, the joints, members, joints, reactions, rotational springs, what else? And S, right? So what is the number of members in this structure?
7.
You count the members from the joint to joint. By the way, if you decided, oh, I'm gonna consider that this member has a joint in the middle, you can do this. But if you consider this is a joint, it's gonna create 2 members, okay? This is valid if you wanna do that. Like if you said, oh, I think this is a joint, I'm gonna call it a joint. You can call it a joint, but once you create a joint, it's gonna divide the member into 2 members. But since you count this as a 1 member, so it has a joint at the start and joint at the end. So okay, I have 1, 2, 3, 4, 5, 6, 7. So I have 7 members. How many joints? 1, 2, 3, 4, 5, 6. 6 joints. How many reactions?
5. I have a question. So let's say that we're doing a test or a quiz, and we have a hinge. Can we take up the hinge and just like take that as 1 member, or
The hinge as a member?
yeah? So
This hinge?
No, like the one that you just put now.
This one?
Yeah.
Oh, this is not a hinge. This we call a joint. Hinge is this one.
Okay.
If you have something like this, is a hinge is a support. Okay. So, but this one, if I big this, I call this a joint, not a hinge.
Okay.
Okay. So this is a joint. If you want to consider it as a joint, you can consider it as a joint. But every support has to have a joint. Like if you have a support here, there's definitely a joint here. and every change broken angle we consider it as a joint. Like if you have a structure something like this, you consider this as a joint. Okay, it's better to do it that way. All right, so, but what if it's something like this, like arched? You can, if you want, like consider this as a joint, you can consider it as a joint, but for me, I would maybe consider this as one member, has one joint at the start, one joint at the end. But if I put something here, I told you that there's a support here, so it's better to consider this as a joint. Okay? All right. Okay, so do you guys remember the rule? IS? What is it?
3M.
3M
3
plus R
plus
RS minus
3
joints plus S. Okay, so 3M is 3 multiplied by 7. Reaction, oh, I didn't calculate the reaction. Reactions, we said it's 5. Rotational springs,
0
0. S,
0
0. Okay, so I have here reactions is 5. Rotational springs are 0 minus 3 multiplied by joint 6 plus S 0. By the way, this is how I want it in the quiz or in the exam. You write the equation and then you solve the equation, because some of you, like last years, they would substitute right away. I have to see what equation did you use, because this has points, okay? All right, so let's say this question is like 10 points. This is gonna get 3, this is gonna get 3. Final answer is 1, and maybe this numbers get 1, okay? So the equations has a big chunk of points. All right, so I have 3 multiplied by 7, 21, plus 5 is gonna be 26, minus 18 is gonna give me 8. So that's 8, okay, 8's statically indeterminate. Let's find out, this 8 are internally or externally, okay? All right, what do you think? How many internal, how many external? Internal is very easy. We know how can I make this structure open. You can open it in many different ways. You can open this and open this. It's gonna be open structure. Or you can open this and this. Or this and this. So you can make it open in many different ways. Okay, let's say I'm gonna open it from here and open it from here. So how many internal forces when I cut in a frame cross section? That's gonna show up. Once I cut here, 3. These 3 are the shear, the normal, and the moment. And there's the same thing from the other side. Shear, normal, and moment. So I have 3 and 3. So I have from this 8, I have 6 internal. Okay, where's the other external ones? If I take this one out, this one has 2. And this frame is gonna be stable under this hinge and this roller. So, and I have out of this, I have 2 external. All right, does anybody have any question? So in the quiz, if I told you, give you a frame, and I told you determine the degree of indeterminacy and show how many is external and how many is internal. So you have to tell me there's 6 external, and sometimes I'll ask you, show me on the frame where they are. So you have to redraw the frame, and you take, and we call this the redundant. So I'm gonna ask you and show me the redundance. Once I ask you to show me the redundance, you have to draw the frame one more time, something like this, this, and I put the hinge, and I put the roller, and I make something like that. All right? This is the stable determinant frame. This frame is a stable and determinant, and it's coming out of this frame after we removed all the redundant forces. What are the redundant forces that this frame doesn't need to be stable? This frame doesn't need the reaction that coming from this support, which is this and this. That's redundant number 1 and redundant number 2. These redundant forces that the frame doesn't need. And these 2 are external. How about the internal? I have this, shear, normal, and moment. Same thing here, shear, normal, and moment. And this is 1, 2, this is 3, 4, 5, 6, 7, 8. I have 8 forces that this frame doesn't need to be determinant, and that this frame, extra forces, that this frame doesn't need to be stable. Okay? All right. So remember, if I ask you to show me the redundant forces, you have to redraw the frame and show me the forces like this. Okay. Let's get over this problem and solve this one. Okay, this one, what do you think? Does it have any internal redundance? This is an open frame. So it's an open frame, so there is no redundance in the members. Mostly it's gonna be reactions or rotational spring. So let's find out. So the first thing that I'm gonna do, I'm gonna calculate the number of members and the joints, reactions, rotational springs, and S. The members 1, 2, 3, 4, 5. So I have 5 members. Joints 1, 2, 3, 4, 5, 6 joints. Reactions, I have 2 here, 2 here, 1 here. So this is 5. Rotational springs, how many I have springs? 1. It's only 1 spring. I see here. All right, the tricky one, S. How many equations that this intermediate hinge is providing to the whole structure? If you guys remember from last time. I have a hinge like this, has a member, 3 members. 2, because S is equal to the number of members minus 1, or the number of n minus 1. So it's going to be 3 minus 1 is going to be equal to 2. Excellent. All right, I have everything right. Believe me, if you got these numbers right, everything's going to be right. If you got these numbers right, you just substitute in the equation and that's it. So the equation IS, 3 members plus reactions plus RS minus 3 joints plus S. So 3 multiplied by 5, reactions is 5, rotational springs is 1, minus 3 multiplied by 6 plus 2. This is going to give me 21 minus 20. It's going to give me only 1. So, and this one definitely is external. So this is verse externally indeterminate structure. All right, can you tell me what should I do in this structure to make it determinant and stable? What is the redundant? What could I remove? By the way, by removing something, that means that once you remove the redundant, the structure has to be stable. Like let's say, for example, you came here and you said, oh, I'm gonna remove this roller and remove this hinge. That becomes unstable structure. So once you remove a redundant, that means the structure has to be stable. Okay? So what is the redundant force that we have here? There's multiple, okay, go ahead.
I have a question. Can there be something like geometrically unstable but stable at the same time?
If something it looks like geometrically unstable, you are gonna see it right away and you will not solve the problem. You are gonna say this is geometrically unstable, and that's it. There's no way that because it's geometrically unstable. And mostly the cases that has 3 hinges on the same line, or for example, I give you like a structure on top of this, a structure, something like this, and on a roller here and a roller here. So once you put a force on this, it's gonna run. It's not stable. So this, at least one of them has to be hinged. All right? Okay, so let's get back to this problem. Let's think about it. Actually, what if, let's say, if I remove this rotational spring, what do you think? The structure is gonna be stable or unstable? Let's think about it. Like if this structure is something like this, and this, and it's gonna be something like this. By the way, this is like a hinge. This is spin. So the thing is, this is how it is in real life. It is something like this. It's like a column here, like this, and this one is resting here, like a frame, and this one is resting here, like a frame. That's how it is in real life. like a column, and this column is supporting this and supporting this. So they are all resting here. So this is a roller. By the way, this roller, this is kind of like a hinge. Okay, so this is stable, and this part is stable. All the frame is stable. If you take this one, you will tell me, oh, is this stable? Yes, this is stable because this is hinge. If this is roller, and you push that way, it's gonna be swinging because this is gonna allow the rotation, and here is gonna allow the translation. So this is gonna rotate. So this is not gonna happen. But since this is hinge and this is hinge, so removing the rotational spring is gonna be, so I can remove the rotational spring and say the redundant is the moment in the rotational spring. Or actually, I can make this, I can keep the rotational spring and remove the roller. Make it like this. You will tell me, oh, is this a stable leaving like this? Yeah, it's a stable. But it's gonna rotate. No, it's not, because you have a rotational spring here. Rotational spring resists the rotation. So basically, this is like fixed, but the thing is, it is not rigid. It's a semi-rigid connection. So deal with the spring that it makes the rotational springs, or she makes the connection rigid, but not that rigid, because you don't know what is the stiffness of this spring. Maybe the stiffness is infinity, and it's gonna be provide a fixation for this support. So what we are saying here, this part is fixed to this part, but if there is no rotational spring here, we cannot do this. If there's not rotational spring here, this one is gonna rotate. It's basically like you're having a structure like this. A structure like this whole thing is gonna collapse. But if you put a spring here, this thing is not gonna rotate because there's something is pulling back the structure. All right.
Can you keep the rotational spring and just add a roller in the middle? So two rollers and one hinge?
Are you in here?
Yeah.
Okay, let's say. Yeah, if you have a roller here, it's gonna work too. And you keep the rotational spring. So, and also you can do it here, same way, because it's a symmetric.
Yeah, right.
Okay. All right, so we are done with frames. So let's switch to something else, which is the grids. I'm sure that most of you guys didn't hear about the grid structures. So let's talk about grid in a little bit. Grid structures. For grid structures are very simple. It's like the structure that we are in here right now. By the way, this building is a 3D structure. But the thing is, we don't solve when we do structure analysis. So if you are working for a design firm that design a high-rise building or multi-story building, this is the steps that we do. First, we take the building floors and we design them separately. Let's say all the floors are the same. Like let's say the second story is the same, like the first, the second, the third, all the stories are the same. Nothing is changing. Same openings, same everything. We only design one floor. And the whole design is gonna apply for all the other floors because nothing is changing. Because our loads that we have here is local on this floor. It doesn't impact the building as a whole. So each floor is taking his own load. So designing this floor is the same like the second, the third, because it's the same design applicable. But let's say one floor has different openings, or one floor has different system, like it's gonna have a flat slab system, one is gonna have solid slab system. We are gonna design them separately. But if all the floors are the same, we design them separately, okay? Once we design the floors, we get reactions at the columns location. Like, let's say there's a column here, column there, column there. We get what's the reaction from this floor in this column. And the thing is, from the top floor, it transfers the reaction to the column underneath it. So that's a one-story loads. But the thing is, when you come to the second story, the columns take the load from the one top and the other one. So you have two stories. So the more that you go down, the more the loads on the columns get doubled. Until, let's say that we have a building 10-story, so the columns at the first story level carry the load of 10 slabs coming from all the floors. So the way that we do it, we deal with one floor and we solve it 1D. We solve it 2D, and we call this as a grid system. Like let's say that this is the floor that we are in right now, something like this. So we put the columns location as hinges, something like this, and let's say that we have columns inside. This is called a grid system. What is special about the grid system, which is the floor system? So deal with the grid and the floor. The grid system only take loads perpendicular on the system, doesn't take loads laterally. So all our loads are going down on the system. Either the live load, dead load, all the loads are going down. It's something like this. All right, and what happened to this system? The thing is, there is no way that this system, as a floor system, is gonna have load like this. Okay, it's not gonna have load in this direction. So it's only have one force reaction going up. So all the force reaction is something like this. There's no X. It's not a frame. It's not something like a frame like this that takes load like this, and you will have an X reaction like this. This thing is vertical, like is in the X, Z direction, but the floor system is in the X, Y direction. So it only have loads going up. All right? How about the other reactions? The other reactions are moment. So let's say this is the floor system that we are in here right now. It's something like this. So the reactions are all vertical, and also there's a moment reaction in X and moment reaction in Y, because this floor want to bend it that way, so the supports want to restrain this bending the other way. So the bending that way, that's another reaction. And also this floor can bend in the other direction that way, and the supports here want to resist the bending in the other way. So all the supports in the grid system has three reactions, one vertical and two moments. And let's talk about the moments more. So the moment is something, okay, so if this, yeah, go ahead.
The grading structures can be applied just to two-way slabs, or are they applicable for one-way slab as well?
One way, two way, any slab system that takes load vertically and doesn't have a load horizontally, that's a grid system. And any system that is going to have this, as soon as it doesn't have loads in the X direction and all the loads in X and Y direction, and all the loads are in the Z direction, is going to be a grid system. Not only the beams, also the slab, not only the slabs, also the beam system. Because the thing is, let's say this is not a flat slab. Do you guys know what a flat slab is? Flat slab is a system. Okay, let's talk about the systems in a little bit. When we design structures, we need to have a structural system. A structural system, that means like all what we see right now is just architecture. Like it's the skin of the building. But behind this skin, there's a structural system that holds this building together. This system is different from building to another. Some systems are concrete, some systems are steel, and even steel or concrete, they have different types. Like some of them with different names. The thing is, we develop a system based on the loads, the type of loads that the building is going to have. Like, oh, this building is going to have a lot of load that way. Oh, we are going to use this system. Oh, this system, we need like a very open space without any columns. So, oh, we need a special system that doesn't allow columns, or that makes me as a structural engineer not add more columns. So, and depends on the load. Let's say I have a gravity loads. The gravity loads has, gravity loads means loads that goes to the gravity. Like our loads going to the gravity. Dead load, the structural load, the chairs load, everything that goes to the gravity is called the gravity loads. That include dead loads and live loads. Dead loads is the weight of the structure and the weight of the flooring, and live load is our own weight, and everything that is moving is a live load. These are all called gravity loads. There is seismic loads. Your structure is like this and the ground is shaking. That is lateral load. Makes your structure makes like this. Wind load, same thing. That is a different load. So to resist the gravity load, every slab system resists these loads locally. Like let's say the floor underneath us, or we are the first floor. The floor on top of us has, I don't know, is fully loaded. This floor doesn't get impacted. This floor has nothing to do with the load on the other floor. Everyone on his own. This floor is on his own, and this floor is on his own. It's acting simply. Let's say that the classroom above us got overloaded, like, I don't know, 500 students got stacked in, and we saw the slab is like bending and it's gonna crack. If this slab got failed and cracked, this slab has nothing to do with it. This is gonna be failed locally. So that's why every slab get designed on its own, all right? So, and that's what is about the gravity load. They only resist the local load on the floor. But the thing is, once this slab get overly loaded, it's gonna transfer the load from the slab to the columns. So maybe the columns over there is gonna get cracked or gonna get overloaded and overloaded the column that takes my load. And if that column gets cracked, this system cannot hold itself. Like, let's say this slab got overly loaded and then transfer the load to this column, and I'm here, and this column is overly loaded, and the column underneath it is overly loaded and cracked, is gonna affect my system. So there is a local system, which is the slab system, and there is a global system, which is the columns and the shear walls that hold the whole structure together. Okay, so that is what we call the component or the of the system that resists the load. Okay, let's go back to the local system, which is the floor system. The floor system take our load. My load is here. Your load is here. So it takes all these loads. And the thing is, this slab had to hold itself. Okay, this slab has to hold itself. Once it holds itself and it take all the load, it transfer the loads to the columns. On the point, and the column here take the load and transfer it to the other column that has the load from this slab and also the slab in the same floor, and keep going to the next column until they transfer the load to the footings or the foundation, and the foundation transfer the load to the soil. That's our job as structural engineers, to take the loads from the slab system to the soil. That's all our mission, is to take the load safely from the slab to the soil. Once we transfer this, once we make this transfer, we are done. And when I mean safely, that every component can take the load safely, like the slab system, take the load and didn't fail, and transfer the load safely to the beams. And the beams take the loads and safely and give it to the columns. And the columns take the load safely and didn't fail to the next column and the next column. Let's say one floor, the columns at one floor, you didn't design them correctly. Even these are safely passed, and this column is not correctly, is not taking the load and failed, the capacity failed to take the load and failed, the whole structure is gonna fail. It doesn't matter if this system was designed properly or not, because columns are really, really important element in the building. But let's say you, in the structure, once you solve the structure and you use SAP 2000, which we are gonna do it later in the semester, and you got one bending moment on the beams not correct, and you design the beam and you put under reinforcement, like it was under reinforced, like the capacity is not going to take the load that is going to come, and this beam failed, you are going to have a local failure in the floor, and you can fix this beam later. So beams and slabs, maybe it's definitely a disaster, but it's not as the columns and the shear wall, because the columns and the shear walls take the whole structure. And definitely the foundation. If you have a problem with the foundation, if you under-design them, and this footing is not taking the whole load, that's a complete disaster. So foundation is the most important component of the building, okay? All right, so let's get back to the gravity load. So the grid system, yeah.
What about like if the building has a lot of redundancy?
If the building has a lot of redundancy, that's good, and that's what we do in structural engineering. But it's still a disaster to happen that you have one of the redundant component is failing. Because the thing is, maybe the structure is not gonna fail, but the cracks is gonna eat your whole structure. So once a footing is not loaded, other columns is gonna get overloaded, and there will be uneven distributions of the load. So you will start to find some diagonal cracks in all the walls that you have. Because the thing is, this column is not taking the load and one of them is taking the load, so you're gonna have differential settlement, something like this, so the cracks is gonna show up. Structure maybe, it's not gonna fail, but it depends actually on where the column is, because sometimes there's progressive failure. One doesn't take the load, so other columns get overloaded, so they are gonna fail, all right? So, yeah. back to the grid system, which is the system that we are in here right now, is gonna take the load. All the loads are vertically, and the thing is, there will be only, since the load all are this way, so the reactions all are this way. Okay, there's no X reactions, and the moments are this way and this way. So let's talk about the moments a little bit. So if the moment is like this, all right, so we can represent the moment with something. Let's say this beam wanna bend that way, and this beam wanna bend that way. So you are gonna have a reaction here that way and a reaction here that way. So sometimes we put the bending moment reaction in that direction. So if I have the bending moment in that direction, we can represent it with a reaction that way. 2 arrows, not 1 arrow. Right? 2 arrows. The arrow's direction follows the right hand rule. If the bending moment bending that way, you make your hand like this, so the arrows are that way. Same thing with this one, is that way, so the reactions are that way. Okay? So let's say if this one is something like this, so I curl my hand like this, so you're gonna have something like that. So that's how we make the bending moment. Okay, so let's navigate what kind of supports that the grid system can have. So the grid system has 3 types of supports. It has spherical, it has cylindrical, and fixation. Fixation is something like this. Cylindrical is something like this, let's say. Something like that. And spherical is like a sphere. Something like this. That is the 3 supports that a grid system can have. But mostly, we usually represent this by hinges. Like if I make this, I represent this as a hinge and represent this as a hinge. But I will tell you in the problem, this hinge is a spherical hinge or a cylindrical hinge. I will tell you in the problem. Okay, so let's see what reactions these supports are gonna have. The spherical hinge is only have 1 reaction, and this reaction is like Fy reaction. Something like that. This thing has Y reaction, Fy, and have 1 moment. What is this 1 moment? Is the bending moment. It resists, it allows the moment, like the moment, okay, we talked that there's 2 moments, but this one resists the torsion. Like you're gonna have something, a reaction like this, like that one. This one resists both reactions, resist Fy and resist the moment in X direction and the moment in Y direction. Like something like this and something like this. So let's imagine how this looks like. So if you have a fixation, like this one is fixed, so it can't go up, it can't bend, and it can't twist. Okay? So that's what happened. Because the thing is, if you have a structure that way and it's fixed here, and there's a load here, what is gonna happen? This one is gonna have a bending moment and also torsion. Because there's a load here, it's trying to twist this a little bit. But the thing is, if I have fixed here, it's not gonna allow the torsion. But if I have a sphere ball here, it's gonna twist. So that's what is the fixation do. This support is like a cylinder. Like let's say my beam is on a cylinder like this. This cylinder is gonna allow this slab to bend, but it's not gonna allow this slab to twist. But if I have a ball here, this ball can allow my system, like let's say I have a ball here, ball support, this ball support can allow this to bend and allow this to twist. Okay? Alright, only thing that this ball can make is resisting this from going down. So it resists the Y reaction, but allows the twisting and allows the bending moment. But once I make this cylinder, it's gonna allow the bending moment, but resist the torsion. Okay, like it's trying to twist, it's not gonna twist it. Okay? Alright, so like think about this cover of the bin is like the ball. So let's say I'm putting a torsion, the bin is twisting. I put bending moment, it's rotating, but you cannot go down. Like if I put a load here, it's not gonna let it go down. But if I hold the bin from here, or I put it on a cylinder, the cylinder is gonna allow to go that way, but it's gonna resist it from the torsion. Okay, that's what happens in the grid system. All right, I'm gonna solve a structure analysis problem on a grid system so that you guys can imagine how this looks like. And actually you will find this problem in the first lecture notes. Let's say my structure, I have a structure like this. And I have a load of 1 ton going down on the support. This is a grid system. By the way, this system is something like this. I have 5 meters and 2 meters, something like that. This is out of the plane, okay? All right, and I asked you to calculate the reactions, find the reactions. Find the reactions and draw normal, shear, and moment. Let's solve it. First, to find the reactions. So what reactions do we have in the fixation? We have 3 reactions. I have a Y reaction. Let's say that this is A, B, and C. So I have YA, and I definitely have a moment that way. This is a torsion. And I have another reaction that way. So this one is going to be a moment like this, and this one is going to be a moment like this. That's the direction of the reaction. I'm going to say that this is MXA, and this is MYA. Let's find these reactions. What is the value? To find the reaction in the Y, so it's still 3 equations. Before we have some Fx, some Fy, some the moment. Right now I have some Fy and some 2 moments. That is the static equation. So let's start by the summation of Fy equal to 0, and I'm assuming that the positive is going up. So what do you think? What is the reaction Ya is going to be equal to? I only have one load, 1 ton is going down. Summation Fy is equal to 0, so Ya minus 1 equal to 0. So Ya is equal to 1 ton. That's a very easy one. All right? Then I'm gonna say that the summation of the moment x equal to 0, and I'm gonna assume that the positive is that way. And this one means like this. So assuming that we are trying to find what is the total moment in the x direction. So I have MXA, the reaction that I don't know, and that is positive because it is in the same direction of my assumed direction. And let's find what torsion that this moment is developing. So if I take the moment at A here, so can you tell me how much MX that this 1 ton is developing?
1 times 2.
Is 1 multiplied by what?
By 5.
Okay, 1 multiplied by 5 is gonna make a moment that way.
1 times 2.
So it's gonna make a moment is in that direction. But to find the moment in the x direction, this one is gonna be 1 multiplied by 2, because this is the moment, like if you take here, so this at a distance 2, so it's 1 multiplied by 2, so it's gonna give you a moment direction in the x direction, in that direction. So this is gonna be 1 minus 1 multiplied by 2, and it's a negative because the 1 is making a moment that way. My positive is that way. So this is gonna be 0, so MXA is gonna be equal to 2 ton meter. Let's go to the other direction. The moment about y, like in MYA, summation of the moment y equals 0, and I'm gonna assume that the positive is this way. Okay, the moment y is the moment in the y direction. So I got the moment in the x direction. So this one, like let's say that is x. So the thing is, okay, imagine with me, this is x, and this is y, all right? So x, this load is behind the x-axis, so in making a moment about x-axis, and the moment is the value of the force multiplied by the arm. The arm is the distance from the x-axis. So the distance from the x-axis is 2, so it's going to be 1 multiplied by 2. And I'm taking the moment about A. So if you take the moment about y, is the distance of the load from the y-axis. So this is the y-axis, and this load as a distance, by the way, 5 meters. Because this is out of the plane inside and these are perpendicular. So it's going to be 1 multiplied by 5, which is the distance of the load from the y-axis. So you are going to have MYA minus 1 multiplied by 5 equal to 0. So MAY or MYA is equal to 5 ton meter. Did you guys got it? I know it's a little bit 3D, and 3D sometimes gets complicated, but imagine with me, this is my structure, and it's fixed here, and there's a load here at distance 1. Okay, so this load is making a torsion on this beam equal to the 1 multiplied by this arm, but is making a bending, considering this one is equal to, like this one and one bend with 1 multiplied by 5, which is the bending. So the torsion is MXA 2 ton meter, and this one is 1 multiplied by 5 is 5 ton meter. Okay, so let's draw the shear, moment, and torsion diagram. By the way, this is, there's no M, there's MX, and MY, or torsion and MY. So what I'm gonna do, I'm gonna draw this 3 times. 1, 2, and 3. All right. So for the shear, it's the same rules. Like the positive one, if the shear is going up and down, this is from the left and the right. For the moment, same thing. Like consider that the torsion as a normal. This is negative. Draw the positive. If the torsion is a negative torsion, positive torsion, it should go outside the cross section, like this. If the torsion is something like that way, and the moment is still like the same, like this one. This is the positive. This is the positive moment. All right, let's go to the shear. The shear is going up, and the value of the shear is 1. So I'm having 1 like this, and it's constant on the whole cross section. And it is positive, and it's 1 ton. Same thing here. This is 1, and you can, by the way, this is supposed to be perpendicular to the cross section, but you know what? I can write it that way. Positive, and this is 1 ton. So the whole cross section is under shear force of 1 ton, and that makes sense because the one, if you cut here and look from the right, so it's going down and it's 1, so it's positive. And cut here, look from the right, 1, cut here 1, cut here 1. If you look from the left, it's gonna be YA and it's going up. So either looking from the left or looking from the right is gonna give you the same answer. It's positive if you're looking from the left and the shear is going up, and it's positive if you're looking from the right and the shear is going down. That is the rule of convention for the signs of the internal forces. Okay, let's look at the moments. Let's look at the moment, which is the moment M about Y. M about Y, the thing is, let's look at this one. The moment here is 0, This one has 0 moment. But once you go away from this load, you are gonna end up with an arm of a moment. 1 is gonna be multiplied by 2 is gonna give you 2 ton-meter. And this is
But wouldn't that be the moment
negative.
about X?
Hmm?
Wouldn't that be the moment about X?
The moment about X? Well, I'm gonna do Y now, and then X I'm gonna do it, which is the torsion.
But 1 times 2,
This is negative, should be down. Yeah, what is your question?
that 1 times 2 is the moment.
Is the moment, not the torsion. This one doesn't have any torsion, this member.
Okay.
This is the only member that has torsion.
Okay.
This member could have torsion if there's another member coming out of it and there's load that making torsion on it. But this load only causes bending moment on this member.
But not about Y, right?
This is the moment about. The thing is, it's not like the thing is once you get to this member, you have to create its own x's. Like you make your x and you make your own y. So let's not think about it y and x. Let's think about it its moment and torsion,
Okay.
because that's moment m and torsion t. So this load is only making moment, and this moment value is negative actually. It's something like this, and this one is negative 2, and this is how it looks like. The thing is, to get the moment here, you're gonna do the same thing. It's gonna be the same load 1, and let's put the same load 1 here. It makes 0 moment here, by the way. You will tell me, oh, but you told me the moment here is negative 2, how it makes a 0 here? Because look, think about it. I know it's a little bit complicated. Okay, it's fixed here, and you have 1 ton here. This one is making moment on this, but the thing is, this section here, at this area, at a distance 0 from this load, when you take the moment, but when you take the torsion, it makes torsion. So, like, when you have these two like this, you have 1, this one is making moment on this one, but the thing is here, the moment is 0, but there is a torsion. And then once you go away from this load, this one is having an arm to make a bending moment on this section. Not sure if you guys can imagine that. Like let's say we are gonna look at this. And let's say that this is fixed here. And this one has another beam that way, and this beam has a load something like that. This load, once you transfer it here, this load is gonna be something like this, and it's gonna make a torsion on this cross section, something like that. So once this load is transferred here, the moment here is equal to 0. It's like you have a beam that has one load equal to 1 ton. And the moment that makes the load that makes here a bending moment, not a torsion, is 0. And once you go away, this moment is getting bigger until you come here. That's the same way that we have it here. Because this load is still at a distance 0 to make a moment at this cross section. Like let's say I have a cantilever like this, and this cantilever has a load here 1 ton. What is the moment here at this cantilever?
0.
0, right? If you put this load here, it's still the bending moment is 0. If you put this load here, here, all this is 0 because I'm taking the moment at this cross section. Okay? What matters is if the load is here. That's okay. So the moment here is 0, but once you go away, it makes bending moment. However, if you have a load here, this load is making torsion at this cross section. What I want you to distinguish is this beam is different from this beam. They have completely different load. You cannot merge them together. Like this one and this one. However, they are completely like the same joint, but they are different. Like if you cut here, there is completely different loads when you cut here. Okay? It's a little bit complex joint, but this is how it works.
And that's creating a moment of 2 ton meter because the connection between the two beams is fixed.
And this one?
Uh-huh.
Yeah, that's like considered like a rigid joint.
Okay.
All right, so, and once you get here, the moment is starting from 0, and the bending moment is gonna go from 0 until you multiply 1 by 5, so you're gonna have negative 5 ton-meter, and this is gonna be the bending moment, something like this. Let's go to the torsion. That's the moment. The torsion is, this beam doesn't have any torsion, it only have bending moment, and this moment is gonna be 1 multiplied by, that's 1 multiplied by 2, that's what we did here.
Yes.
But torsion-wise, this has 0, there's no torsion. But this beam exert a torsion on this beam, and the torsion start from here, and it's equal to 1 multiplied by 2, and it's a negative torsion. Look at this. This beam is gonna be something like this, so the torsion is gonna compress the section, and we are looking from the right. So it's gonna be negative 2. Let's say this cross section was in the other side, so it's gonna be an opposite direction. It's gonna be positive, but since this piece is outside, so it gives you a negative torsion. And same, the torsion is gonna be constant on the whole cross section, negative 2, because if you take the torsion here, it's gonna still 1 multiplied by 2. If you take it here, it's still 1 multiplied by 2, so it's gonna be negative 2, and this is the torsional force diagram. It's a little bit tricky, but if you go and focus and try, the main point to understand this example is to distinguish between this one and this one. These are two completely different cross sections, and each one has completely different internal forces. Okay? All right, so this is grid-wise, how to solve the grid using structure analysis. Let's actually see how we can determine the degree of indeterminacy for these grids. Okay, let's start with a simple grid. If I told you I have a grid supported by a hinge like this and supported by fixed like this, and I ask you to calculate the IS, assuming cylindrical hinges. Like this hinge is cylinder, okay? What is the IS is gonna be? You are gonna solve this like solving any of the frame questions that we had. First, you have to calculate the number of members. What is the number of members?
2,
What is the number of joints?
1, 3.
Joints, 3. What is the number of reactions? By the way, this is fixed, 3, and this is cylindrical, so it's gonna have 2. So 3 plus 2 is gonna be 5. Rotational springs, 0. S equal to 0. All right, if you guys remember the rule, IS is gonna be equal to, same like frame. And same like frame, but the thing is, the variables here are different. The member, each member has 1 shear and 2 moment, but the frame has 2 forces and 1 moment. That's the only difference. And the reactions definitely are different. So let's apply the equation. So you're gonna have 3 multiplied by 2 plus the reaction 5, RS is 0, minus 3 multiplied by 3. So this is 6 plus 5 equal to 11, minus 9. So I have to, tell me, is these two are internally or external? External, no internal because there is no closed loops, okay? Can you tell me what are the redundant forces that we can remove from this system so we can make it stable and determinate? I can remove that hinge, right?
Yeah.
If I remove that hinge, this fixation can take it. So the redundant forces are this reaction and what else?
DX.
The cylindrical is, yeah, this moment, M, X, or the torsion. Okay, so these the two Ikisor reaction that this support doesn't need. So if I ask you in the exam or in the quiz, determine the degree of static indeterminacy of a structure and show me the redundant, you have to draw this again and draw the forces. If, for example, you draw the forces wrong and you told me, oh, the redundants are the 2 moments, you're gonna lose point. what if you didn't draw anything, you are gonna lose maybe half of the problem. So you have to draw the redundancy and show me, because that will show how you understanding your, like how you, what is the level of understanding of the whole topic. That the structure, what does indeterminacy mean? Indeterminacy means that the structure doesn't need these reactions to be stable. So if you don't know what are these reactions, so you don't understand anything. Okay, so let's put this back. All right, let's make this a little bit more complicated. All right, I have this. Okay, I have this intersection between two grids. Number of members, can you guys tell me? 5. 1, 2, 3, 4, 5. Number of joints? 1, 2, 3, 4, 5, 6. The number of reactions. By the way, all these are cylindrical hinges. 2, 4, 6 plus 3 is gonna give you 9. And S is equal to 0, RS is equal to 0. So I'll substitute in the equation, IS equal 3M plus reactions plus RS minus 3 joints plus S. So IS is going to be equal to 3 multiplied by 5 plus the reaction is 9 plus 0 minus 3 joints are 6 plus 0. So 15 is going to give you 24 minus 18 is going to give me 6. And they are all external. Can you tell me what are the 6 reactions that this structure doesn't need? I can remove the hinges. This one, and this one. So basically I'm gonna have 1, 2, 3, and the moments. And the moments are the torsional moments. Like this one is not gonna have, like this is the torsional one, and this is the torsional one, and this is the torsional one. Because the cylindrical hinge resists the bending moment, which is the one perpendicular. Look at this. This is my beam. The cylindrical doesn't allow the torsion. Okay? But allows the bending moment. Okay. All right, so that's for these ones. All right, with this, that's actually, I covered how to determine the degree of static indeterminacy for all the structures. Trusses, beams, frames, and grids. All right? So let's shift to another topic. Is called the degree of kinematic indeterminacy, and that's way much easier. Degree of kinematic indeterminacy. So the degree of kinematic indeterminacy is much simpler than that, and that's basically is we want to know what is the degrees of freedom that our structure has. And this is a very important concept when we come to the stiffness method. Because the stiffness method is all about the degrees of freedom. Okay? So basically, the degrees of freedom, think about it. Like, let's say this is a structure member in the air. This is a structure member, if it's in the air like this, is it stable or unstable? It's unstable. It has 6 degrees of freedom here and 6 degrees of freedom here. These freedoms are X translation, Y translation, X translation, Y translation, and Z translation. And it can rotate about X, can rotate about Y, can rotate about Z. That is at this joint. So every joint in the space has 6 degrees of freedom, 3 translation, and 3 rotation. Like, think about it. This is my structure. So this one is gonna have this, this, and that, and rotation about this, rotation about that, rotation about this. Same thing, 1, 2, 3, rotation, rotation, rotation. So every member in the space, that's a space, not 2D, has 6 and 6. And if a member has degrees of freedom, like it's totally free at the start joint and totally free at the end joint, that means this structure is unstable. Okay? Alright? In our applications, we cannot give this freedom for our structure element. Basically, we create the non-freedom for the elements. Why? Because we need them to be stable. If this structure is free, we cannot sit in it, right? So that's why we need to count the number of degrees of freedom for the structure, because this is the source of deformation. If I have a joint that is not free, like let's say this joint is not free, that means there is a deformation at this joint, and we need to calculate this deformation and see if it's allowed and it's gonna make this structure comfortable to stay in. And so we are gonna allow it, and we are gonna say, oh, the structure is like the degree of serviceability of the structure is in compliance with the code. All right? Like let's say I have two members, like this one, and I try to connect them, and I'm gonna make them as a support for this slab from the middle. So that means there is a degree of freedom that happens in the middle between them. It's okay to have a degree of freedom, but isn't within the allowed or not? So that's what we need to figure it out. But to figure it out, we need to find out how we can determine the degrees of freedom of the structure. So the degrees of freedom of the structure, we call them IK, and we call it kinematic indeterminacy. Like K is coming from the kinematic. S is coming from the static. So for plane truss, space truss, plane frame, space frame, great. Okay, so for plane truss, the IK is equal to 2 multiplied by the number of joints minus the reactions. That's the degrees of freedom. And let's think about it. For the truss, if you have a truss like this, each one joint on this truss has an X translation and Y translation, X and Z. Like, let's think about it. You have a joint of truss. So if this truss has a load, this joint of the truss can move this and can move down. The trusses, the 2D trusses cannot move in the 3D. We're coming to the 3D in a little bit. But it only have X and Y translation. 2 translations. Okay, what that restrain this translation? These 2 hinges is the only 2 supports that restrain translation for this truss. You have 2 here, 2 here, 2 here, 2 here. Here you have 0. Here you have 1. Because this one restrains the X, the Y translation, but allows the X translation.
What do you have 0?
I have 0 here because this one doesn't, this is a hinge. Doesn't allow X and doesn't allow Y.
Oh, 0.
Yeah, because if I put a hinge here, this one is gonna lose the 2 degrees of freedom that it's gonna have.
Oh,
If I put a 1 here, it's gonna lose the 2 degrees of freedom. But if I put a roller here, it's gonna lose only 1 degree of freedom.
Got it.
Okay. So the space truss is a little bit different. The IK is 3J minus R. Why? Because right now it's a space, so it can move 3 translations, X, Y, and Z. So 3 multiplied by J, each joint has 3 movement. So minus reaction. Plane frame, IK is equal to still the 2J, however, I'm gonna add S minus R. Why is that? Like why I added, sorry, this is 3 still. I'm gonna tell you why it's this 3. If I have a frame like this, let's say I have this joint have 3 movements in a frame. It's different from the truss. This joint can move X and can move Y and also can rotate. Alright? So this joint can rotate and can move X and can move Y. So you have, let's actually write on top of each one. This one is X and Y movement, this is X, Y, and Z. And this one is X, Y, and moment. Rotation. Let's say not moment, let's say theta. That means it can rotate. How about S? Why did I add S? Because S add more freedom to your structure. Let's say, okay, let's say this joint. I'm gonna say that this is the joint. By the way, you can make as much a joint as you want. Like let's say I'm gonna make this as a joint, but it's better to make the joints are the one like this one and this one. But let's make, actually let's make that one as a joint. And I'm gonna make this one is an intermediate hinge like this. So before, this frame was something like this. For this one has 1 degree of freedom in the X, 1 in the Y, and actually can rotate, 3 degrees of freedom. But what I did here by putting intermediate hinge, look what I did. I still have the X, and I still have the Y, but this one can rotate, and this one can rotate in a completely different rotation from this one. So I make this one and this one have separate rotation, so I added more degrees of freedom. Okay, before they were connected together, so we either, both of us rotate that way or rotate that way. So we only have 1 rotational degrees of freedom. But once you put an intermediate hinge, you make this one rotate that way and this one can rotate that way. So they can have separate rotations. So I added more degrees of freedom. So the more that you add intermediate hinges, so the more that you're gonna have degrees of freedom. And it's still, S is counted the same way that we were counted over there. If there's multiple members connected to it, like let's say you have a connection like this. This connection, if it's rigid, so we either rotate together or we stay together. So it's only 1 rotation. But let's say I put something like this. This one can rotate separately, and this one can rotate separately, and this one can rotate separately. So we added more degrees of freedom. So that's why we put S here. And by the way, look at this. S before was in the other side. Right now it's on the other side because over there we are looking for the redundance, more restraining. Here we are looking for more degrees of freedom. All right, for the space frame IK is equal to 6 multiplied by joint plus S minus R. Right now, if you are in the space, before for a space thrust, we're only looking at the translation. There is no moment at the thrust. Why? There is rotation, but there is no bending moment because the trusses have 0 bending moment. They are all normal forces. But in the space frame, there is X, Y, and Z translation, and there is rotation in X, rotation in Y, and rotation in Z. That's what happens if you have a space thrust. So if you have a space thrust, this joint can, like here, can move X, can move Y, can move Z, and can rotate about X, can rotate about Y, and can rotate about Z. So each joint has 6 degrees of freedom, 1 plus S minus R. Grid is the same like frame. Is going to be IK equal to 3 joints plus S minus the reaction. But the joint right now has Y movement, and the rotation is theta X and theta Y, because you have 2 rotation and 1 translation. In the frame, you have 2 translation and 1 rotation. Does anybody have any question?
A spring wouldn't resist.
The spring actually doesn't resist the degree of freedom. Like if you have,
just limits it.
it's limit, but you still have the freedom. Like let's say I have a member like this. How many degrees of freedom is this member has? All the degrees of freedom here, right? So let's say that this is a 2D frame, so it has 3 degrees of freedom here. If you put a spring here, you still have 3. But if you put hinge here, you only have 1, the rotation.
Correct.
But let's say that you put roller, so you only have 2 degrees of freedom. If you replace the roller with a spring, so you get your 3 degrees of freedom, because this point is gonna move. It's gonna make
Okay.
something like this. And let's say I put the spring that way in the X direction and a spring on the other way. So I restrain a little bit the movement in the X and the Y and the Z, but there's still some movement and there's still 3 degrees of freedom here. So springs, when we calculated IK, doesn't affect the degrees of freedom because they allow the rotation. All right? So that's it for today. And next time we're gonna have some application on IK, and I'm gonna make the homework deadline. I'm gonna extend it because I need to finish the whole topic. So I'm gonna make it. I'm gonna make the due date maybe by the end of next week. That's for the homework. We're gonna have quizzes on all the stuff that we had right now, not on the. Let's make the quiz on Monday next week. All right? So
Tuesday.
Tuesday next week. All right? Okay.